We're going to get into the motor system proper today. We've been up the sensory side. We've talked about some of the reflexes in the postural system, and we're going to go down the motor system now, or at least the neurons go down the motor system. Now, the first two slides that I'm going to show you are the two most important slides that I will show you in this entire lecture course. A lower motor neuron has its entire neuron in a single embryological segment of the body. If it is a sixth lumbar segment, lower motor neuron, its entire being is in the sixth embryological segment. But within that segment, it has bits in the central nervous system and bits in the peripheral nervous system, and it forms the motor neuron of the peripheral nervous system. And its cell body is in the ventral horn of the spinal cord, in lamina 9. Good, yes. So if you see a neuron with a cell body in lamina 9, its entire neuron in a single embryological segment, and part of it in the central nervous system, and part of it in the peripheral nervous system, it's a lower motor neuron. An upper motor neuron is confined entirely within the central nervous system. It doesn't get out into the peripheral nervous system. But it does traverse segments and areas of the central nervous system. So it might be an upper motor neuron to, well, I don't know, lumbar 6 again. And it might have a cell body in the primary motor cortex of the cerebral cortex, and its axon might go through all those embryological segments between the cerebral cortex and the sixth lumbar segment on the way down. But it will not leave the central nervous system. And an upper motor neuron is usually inhibitory. Something like 80% of our upper motor neurons are inhibitory. And they inhibit lower motor neurons. So we've got this concept of a reflex arc setting the basal tone in a muscle, and an upper motor neuron inhibiting the lower motor neuron to reduce tone in that muscle group so that the opposing muscle groups can have an activity by relatively increasing their tone. So that, for example, if we reduce the amount of tone in our flexor muscles, we get an extension. We're not usually consciously contracting the extensors to get that extension. We're relaxing the flexors and allowing the extensors to do their thing. These are the neurological signs that you would associate with a lesion of either an upper motor neuron in red or a lower motor neuron in blue. Whichever of those neurons is affected, you will get paralysis or paresis, which is partial paralysis. But there are major differences between lesions in those two neurons, which will almost always allow you to diagnose which of those two neurons is affected. So, for example, with upper motor neuron lesions, there is increased muscle tone. It's a spastic or hypertonic paralysis. With lower motor neuron lesions, there is absent or decreased muscle tone. With an upper motor neuron lesion, there is present or increased reflexes locally. So things like the patellar reflex, the triceps reflex, all those reflexes are either present or increased. But with lower motor neuron lesions, the reflexes are absent or depressed. And finally, muscle atrophy is minimal with upper motor neuron lesions. You will get some, especially in conditioned animals, because they're not able to move the limbs and so they're not able to exercise. But with lower motor neurons, the muscle atrophy that you get is severe. There is nothing like the muscle atrophy that you will see with a lower motor neuron lesion after the first 4 to 6 days. It takes about a week, and then the muscle mass just falls away to nothing, and the animals become literally skin and bone in the area that's affected. Now, a few things to say about this. You can work all this out if you understand the concept of a reflex arc that is affected by an inhibitory upper motor neuron. It all makes good sense. If you cut the lower motor neuron, you cut the innervation to the muscle, you take away that reflex arc. And as I've told you a couple of times already, the lower motor neuron is the final arbiter of contraction of its muscle group. And so if you cut that lower motor neuron or damage the lower motor neuron, there can be no contraction in that muscle group. The muscle won't contract spontaneously on its own. And so with lower motor neuron lesions, you get absent or decreased muscle tone, no reflexes because the lower motor neuron can't carry that reflex information to the muscle, and the muscle atrophy is because muscle tone is not only analogous to use in the exercise sense, but also use in the electrical depolarization sense. And if a muscle is not getting the background electrical activity that it gets from its lower motor neuron, even when you're not using the muscle, then that muscle will begin to atrophy rapidly and hugely. The upper motor neuron is affecting that reflex arc, but it's not destroying the reflex arc if the upper motor neuron is damaged. And so you get a disinhibition of the reflex arc. And so muscle tone tends to be increased, especially in the extensors, and we tend to get this kind of extensor rigidity. Local reflexes are increased because there's no inhibitory damping down from the upper motor neuron to reduce those reflexes. And because the link between the muscle and its lower motor neuron is still intact and it's still getting that basal electrical activity from the lower motor neuron, muscle atrophy is minimal. Hopefully you will remember from last semester when we first looked at Horner's syndrome. We looked at primary, secondary, tertiary Horner's syndrome, and I said that the degree of severity of a lesion is related to the proximity of the lesion to the effector site. You guys remember that? This is another really class example of that, in the sense that the nearer to the muscle is the nerve damage, the more profoundly abnormal is the muscle's function. But the more localized is that abnormality. So if you get lower motor neuron damage, you get a very, very profound change in function. Muscle tone abolished, reflexes abolished, muscle wasting huge. But it's only related to those areas where that lesion is innervating. So if you cut, say, the femoral nerve, it will just be the muscles innervated by the femoral nerve. If you damage a spinal cord segment and destroy lamina 9 of a spinal cord segment, it will be just that segment that is affected. But the altered function is very profound. For upper motor neurons, the change in function is less profound. Still got muscle tone, but we've altered it, it's increased. Still got reflexes, but we've altered those, they're increased. And got some muscle atrophy, but not as much muscle atrophy, not anything like as much as with lower motor neuron disease. But the area of damage is wider. If you have an upper motor neuron lesion in the thoracolumbar spinal cord, then everywhere distal to that is affected. You can pin down the level of a lesion by looking at the relative effects of the lesion on the limbs. So, for example, a spinal cord lesion at the upper thoracic or more likely lower cervical level, at the level of the brachial plexus, will take out lower motor neurons to the forelimb and will take out upper motor neurons to the hind limb. And so you will have a flaccid, areflexic paralysis of the forelimb and a spastic, hyperreflexive paralysis of the hind limb. You've got lower motor neuron disease in the forelimb, upper motor neuron disease in the hind limb, and you can say, oh, the site where those neurons come together is that segment of the spinal cord. That's where the lesion is. That's where we need to look for the lesion. Okay? So it's a good example of neurophysiology and neuroanatomy giving you the location but not the etiology of the lesion. It doesn't tell you whether you've got a space-occupying lesion, a neoplasm at that level of the spinal cord. It doesn't tell you if there's a fractured vertebra or a prolapsed vertebral disc or an ischemic lesion like a fibrocartilaginous embolus. It doesn't tell you what kind of lesion you've got, but it tells you where to look for it. Okay, there are three motor systems that we're going to look at. We're going to look at the pyramidal system, the extrapyramidal system, and the motor feedback systems over the course of the next two lectures. But first of all, I'm going to tell you that the difference between the pyramidal system and the extrapyramidal system is more and more seen as being artificial. Textbooks that were written 10, 15 years ago have this pyramidal system, extrapyramidal system, and it's like medicine and surgery, and the two shall never meet each other in the corridor. Big differences. Different functions, different ways of working, different things. But more and more we're seeing that these are actually just part of an integrated motor system. And the reason for differentiating between them is historical. And so the pyramids were found a long time before we knew what they did. They're huge, great, pyramid-shaped things on the ventral surface of the brainstem, pyramids, okay? And then it was found that motor fibers go through them. Pyramidal motor system, great. And then we found all these other systems that had nothing to do with the pyramids. Oh no, what are we going to do? Extrapyramidal motor system, cool. And so now we've got these two motor systems that are actually kind of working together to do the same kinds of things with subtle differences between them. And we're stuck with calling them the pyramidal system and the extrapyramidal system. And it's kind of artificial. The importance between them is greater for the primates than it is for the other mammals. And so when we're looking at the domestic mammals, largely speaking, the pyramidal system is a very small also-ran system. And the extrapyramidal system is a big, important motor system. Let's have a look at that. Here is a primate, or drawing of a primate. And here is a representation in yellow of its extrapyramidal system and in red of its pyramidal system. And you can see that, relatively speaking, the pyramidal system has more importance in terms of motor function than the extrapyramidal system. And it's all about this opposing digit here. Okay? If you want to know why, blame your thumb. Because it's that prestidigitation, that ability to work with our fingers and to do things and to use tools that requires us to have a really well-developed pyramidal motor system that can give us that degree of function in our hands and our fingers and in our toes if we're chimpanzees or whatever. So the primates have this really well-developed pyramidal system. If you're a horse, this is the balance between your extrapyramidal and your pyramidal nervous systems. And you can see that the pyramidal nervous system, not really vastly important. Yeah? Almost no pyramidal fibers going beyond the cervical region. Look at the carnivores. The carnivores are a kind of halfway house. Yes, they've got an extrapyramidal system, and yes, they've got a pyramidal system, but the pyramidal system is not that important. It's there, and it's useful to them, especially around the head and the neck, but it's not a particularly useful system. And again, most of their movements are coordinated movements. You'll see cats kind of be able to move one leg quite precisely, but it's usually a postural movement. They don't usually extend their leg like this unless their claws are going like this at the same time. It's all a together sort of thing. So they can't do that or do that or do that. They don't have that dexterity of movement. They don't have the need for it. So when we're looking in a veterinary sense, the extrapyramidal system is much, much more important. It's the major motor system. But when we're looking in a neuroscience or a medical neurophysiology book, then it's the pyramidal system that gets the major billing as the major motor system, because it's your major motor system. And so again, be aware of the species differences between the two. Given that these two systems are a kind of a spectrum of different motor function, I'm going to pretend that they are two different systems in order to highlight the differences between them to give you an indication of how they work. So, what have we said so far? The pyramidal system is thought to control precise movement. It's well developed in primates and man, present in carnivores, and only gets as far as the cervical region in ungulates. Now, when I say it controls precise movement, do not think that when you're playing the piano, the extrapyramidal system is not doing anything, because it's giving you the posture, it's giving you the balance, it's giving you the reach so that when you move your arm that way, suddenly your whole body doesn't jerk that way. Everything is coordinated. It all sits together. But the pyramidal system is the only system that connects your primary motor cortex with your muscles. It's the same neuron all the way down. Let's have a look at that. Here is another dead spider diagram. With apologies, this is a diagram of the pyramidal motor system. And we've got slices through the cerebral cortex, the midbrain, the medulla, and the cervical spinal cord. And if I had a sticky thing to point with, I will be able to show you that these structures on the ventral surface of the brainstem are the pyramids. And you can see they get wider as they go up. You can imagine them narrowing down. And down here in the cervical spinal cord, this is the kind of vestige end of the pyramids. This tract goes all the way up, getting wider and wider and wider. And you can see that just like the medial lemniscal system, between the pyramids and the cerebral cortex, the motor cortex this time, there is a swap over in the direction of the somatotopic localization, such that down through the pyramids there is a craniomedial localization, but in the cerebral cortex there is a craniolateral localization. And you will remember that in the sensory systems that's exactly the same between the thalamus and the cerebral cortex, and hopefully you'll remember that it's an embryological thing because the cerebral cortex kind of folds over in its development. Yeah? The difference is that this time in the pyramids it's the same upper motor neuron going all the way down and synapsing with neurons in the same segment of the spinal cord as the lower motor neuron, probably in laminae 7 and 8. Notice that this is a contralateral system. It decussates. Notice that it decussates in different places. The vast majority of the system decussates in the medulla, but some of the system decussates in the segmental spinal cord. Again, very similar to the medial lemniscal system, where the fibers of the dorsal fasciculus decussate in the medulla and the fibers of the spinothalamic tract decussate in the segment. Yeah? So it's very similar to the major sensory system, but it's the other way up. The fibers are descending this time. So we've got the cerebral cortex at the top. Oh, yes. Notice in the midbrain, midbrain, brainstem, that the lower motor neurons of the cranial nerves are ipsilateral structures, and the upper motor neuron is decussating to get to, in this case, the lower motor neuron of the third cranial nerve. So we've got a kind of a segmental decussation there. It's similar to what's going on down here, but the difference between the spinal tracts and the cranial nerve tracts is that the cranial nerves don't have this bulk decussation in the medulla because the cranial nerves come off prior to that bulk decussation. So there we've got the lateral corticospinal tract, the pyramids, and down at the bottom, the ventral corticospinal tract. This is a section through a sheep's brain, or through the remaining part of a sheep's brain. This is a sheep's brain dissection that I do with science students, and so there isn't a great deal of brain left at the moment, but basically ventral is this way, dorsal is that way, rostral is that way, and caudal is this way. And the brainstem, if it was still here, would be coming off here and going down here. These are the crura of the cerebral cortex, the things that support the cerebral cortex and attach it to the brainstem. This is not a midline sagittal section, it's about 5 millimeters to the side of midline, so it's 5 millimeters in. You can see the cerebral cortex, the grey matter over the top. You can see that these grey matter blobby areas here in the corpus striatum are many of the basal nuclei, which we will meet later on in this lecture. And can you see the white striations that are going through that corpus striatum? The things that give it the name, the corpus striatum, the striped body. Those are the myelinated neurons of the pyramidal motor system, going down from the cerebral cortex, gathering into a white bundle here, and becoming the pyramids down here and going on ventrally through the brainstem. So those are the same neuron going all the way down from the motor cortex to the segment of the spinal cord. Some of the longest neurons in the body in primates. And you can see from that that we can localize those pathways and localize those structures. And you can also see or imagine that the cerebral cortex has kind of started down here and folded over that way. Can you see that kind of radiating, folding over feeling that you get from those fibers? Yeah? They've kind of started down the bottom and they've been dragged upwards. This is a CT scan of a German Shepherd that I saw, whoa, when did we see this dog? It must have been 92 maybe. Maybe, yeah, 92 probably. So a few years ago now. Well, fairly obviously, this is a section through the pharynx here with an endotracheal tube here, the nasopharynx just above it, and the cranial vault just above that, locked into the skull. Can you see that white area within the cranial vault? Yep, that's a space-occupying lesion. It's a tumour, a neoplasm. And this tumour that we found led us to do a craniotomy on this dog and to resect the area of the right cerebral hemisphere that had the tumour. And when we got in, we found that it was quite extensive, and we ended up taking out the whole of one cerebral hemisphere. We took this dog out from surgery, we got it into intensive care, and the dog woke up, and it circled a bit for about 2 days, no surprises there. And on the third day, it stopped circling, and we thought, well, today's the day, we'll let the owners back in, we'll see what they think. And we nervously let the owners in to pet the dog and play with it and have a pat with the dog. And the owners said, "Thank you so much. You've given us the dog that we had 6 months ago back." Take-home message, you don't need a lot of cerebral tissue to be a dog. But in terms of motor function, what happens if you get a lesion of the pyramidal system? Because for this dog, we've taken out 1/2 of its pyramidal system. All those neurons with the cell bodies in the motor cortex on that side, gone. This is a quote taken from a fairly old and reasonably nasty physiology paper. After experimental destruction of the motor cortex, a dog is able to walk, choose one food from another and eat it, and respond to stimuli appropriately, should be in there, by barking or growling. Okay, what else do we expect from a dog? Not a great deal, really. There is some circling initially, and then some hypertonus, some spasticity, and some hyperreflexia. Yeah? A small degree of an upper motor neuron lesion. But there is not the kind of lesion or the kind of loss of function that you will see with a spinal lesion. The lesion that you get is subtle. Okay, let's go on to look at the extrapyramidal system. The definitions are a bit confused. So if you ask a neuroanatomist what it is, they will say it's any motor system other than the pyramidal tracts. And then you say, well, what about the vestibular motor system? And they go, oh, no, of course not. That's not part of the extrapyramidal system. We mean anything apart from that. So people kind of know what they mean when they're talking about it, but it's not easy to define it. And the reason that it's not easy to define it is because it's very diffuse and it's very scattered throughout the brain. It's a system of different areas of the brain that function together to give us a coordinated motor function. And so it tends to initiate and regulate complex motor functions. Things like walking, running, jumping, riding a bike, riding a horse, all those complex motor functions that require you to do lots of things together. They tend to be functions that the extrapyramidal motor system would put together in this huge diffuse network of neurons that we'll see in a minute. It's centered around the basal ganglia. The basal ganglia are a series of many ganglia that you will see around the base of the cerebral cortex. The red nucleus, the tectum, the substantia nigra. There's 50 or 60 different nuclei that are centered around the base of the cerebral cortex. We call them the basal ganglia because it's easier than trying to remember all their damn names. And it feeds back into the pyramidal system. It doesn't work to the exclusion of the pyramidal system. The two systems work together. So it's possible to look at the pyramidal system as just another feedbacking network of the motor system generally. But largely speaking, the textbooks don't do that at the moment. There's probably a move towards that, but it's not there yet. So these are some of the more important blobs of the extrapyramidal system. And I've put them, loosely speaking, into place just to give you an indication of how they work together. Here are the names of the grey blobs. And again, they're not all on there. Some of them, like the globus pallidus, in yellow here, laterally, just below the cerebral cortex, is actually a collection of grey blobs. And if you look in textbooks for the medullary nuclei, you'll probably find 6 or 8 of them named. But there's only a certain degree of complexity that we need, and even this is more complexity than you actually need. I'm just giving you these dots to show you in a moment how the whole system works together as a coordinated system. So, let's have a look at some of the connections between these areas and look at how they get to the gamma and the alpha motor neuron, and also look at whether they are inhibitory in green or excitatory in red. So first of all, we've got some functionality coming out of the primary motor cortex. It's coming into the globus pallidus, and it's spreading down to the vestibular nuclei, down to the substantia nigrum, down to the nucleus rubris. And then we're starting to get feedback. Even at this early, very high stage, we're getting feedback between these individual structures. More dead spiders. All these lines feeding between themselves, passing information around. And remember, at every stage that these neurons pass information to another center, there is information processing going on. That's what it's for. That's why we do it. So this processed information is being passed round and round and down through the motor system until we get to the stage where we start to get output to the lower motor neurons. Here it comes from the reticular formation, from the medullary nuclei, from various centers through the brainstem. Oh, one too far, I always do that. And also from the vestibular nuclei. Remember that the vestibular system is the ipsilateral system. It doesn't decussate. Yeah, it comes down to the same side, and that's why I've drawn it as the only nucleus on that side of the diagram. All the other systems decussate. And so all the other systems give us this complicated and integrated network of neurological information coming down to the spinal cord. So what's it all about? You'll remember in the second lecture I showed you some diagrams taken from a spinal cat and said that if you take a cat and cut the higher centers of its central nervous system off its spinal cord, it's still able to walk, and it's still able to generate that walking gait when you move a treadmill under it. Well, let's look at some of those higher centers now. Here we've got sections of a cat's central nervous system from the midbrain at the top down to the spinal cord at the bottom. And this is going to be lower cervical or upper thoracic spinal cord. It's going to be spinal cord where the brachial plexus feeds out to the lower motor neurons. And in green, I've filled in the areas which are responsible for processing information which allow the animal to walk. The area at the top is called the mesencephalic locomotor region. And it sits at the top of this extrapyramidal system and says, hey, walk. I don't know where. Cerebral cortex told me, just walk. Okay? So again, if it's us, well, we might think this is our volition, our cerebral cortex saying, let's go to the pub. More likely, it's the thirst centers in the hypothalamus saying, need a drink. And the cerebral cortex says, I know, let's go to the pub. And passes walking information down to the mesencephalic locomotor region, and that says, we're walking, guys, must be going to the pub. Okay? But the different areas of the central nervous system are dealing with their information in an appropriate way to bring about function in the whole animal. If you place an electrode into the mesencephalic locomotor center, a stimulating electrode, and you begin to stimulate it, if you stimulate it with a low amplitude signal, you will get a slow walk. And as you increase the amplitude of the signal, the walk will get faster and faster and faster. But look at this, as it gets faster, the gait changes. Because at a walking gait, we've got this reciprocal gait. And then in the cat, as the gait gets faster and faster, it gets into a trot and then into a gallop. And the legs change from a reciprocating gait to a gait where they're both working together. Okay? The mesencephalic locomotor region doesn't have anything to do with that. It's just saying, walk this fast. And all those lower centers in the brainstem and down to the spinal cord are interpreting that signal from the mesencephalic locomotor region and saying, oh, I'm responsible for this leg, I'd better extend now and flex now and extend now and flex now because that's what I'm supposed to do. And integrating that signal with other ones so that at an appropriate gait, this is happening, and then as the gait changes, this starts to happen. It's all happening further down. So that all the mesencephalic locomotor region is doing is saying, I've been told to walk, we're going to do it this fast. And the lower centres turn that into an appropriate set of motor activities that make the animal behave in its environment as the animal wants to behave in its environment. Or more likely as the animal's hypothalamus is telling it to behave in its environment. Lesions of the extrapyramidal system. We tend to get things like tremor and involuntary movements. We get alterations in posture and muscle tone. And we get something that the medics call a poverty and slowness of movement. Okay? Any of you know anybody that has got or has had Parkinson's syndrome? Yeah, a few hands go up. Okay. That is a classic lesion of the extrapyramidal system. Okay? And those signs that you get, that altered posture with the stooping gait and the resting tremor and the kind of slowness and paucity to be able to do things, those are the lesions that you get with extrapyramidal motor systems. The tremor with the extrapyramidal system classically is a resting tremor, i.e. it's a tremor that comes on when the person or animal's doing nothing, and then it disappears when they do something, and then when they're not doing anything again it comes back. And I want to contrast that to a tremor that we'll meet in the next lecture, which is an intention tremor, which comes from the cerebellum. That's a tremor which is absent when the person's not doing anything, but occurs whenever they try and do something and then goes away again when they're resting. So with the basal ganglia, the tremor is a resting tremor, present at rest, usually absent when trying to do something. And the actual activity or the ability to do something is really difficult. It's slow, it's usually under-expressed, but actually the animal can do all the things that a normal animal can do, it just can't do them as well. Another example of a lesion being a long way from the effector site, it's right at the top of the motor system, having effects that are not that abnormal. This animal can do all the things that a normal animal can do, it just does them a bit differently and a bit more slowly and with more difficulty, but it affects the entire body. So that posture, that change in posture, is a global change in posture. It's the entire body that's affected.